Hello and welcome. This is SFU Math 152, Calculus 2. My name is Brenda Davison. This is section 7.1, integration by parts. So take a look at that problem there. We want to integrate the function x e to the x dx. And right now we may not be able to see how to do this. Substitution doesn't work, and that is, as of yet, our only tactic, really, besides being able to do it by inspection. And substitution, let's just remind ourselves, basically substitution corresponded to reversing the chain rule. So I'm just going to make a note of that. Substitution is equal to like a reversal of the chain rule. And so we were using it for composite functions. We had to sort of see that indirectly, but that's what we were doing. So that was our first method. And now we have a problem to integrate this, and it's not, we don't obviously see the derivative of one part of the function somewhere else. So we have a different method for this, and that is going to be integration by parts. Okay, so we're letting f and g be differentiable functions. Then the integral of f of x g prime at x dx is f at x times g at x minus the integral of g of x minus f prime at x dx. So that is the basic rule for integration by parts. Oftentimes we use u to represent f of x and v to represent g of x, and then you sort of can maybe say this to yourself easily, that the integral of u dv is equal to uv minus the integral of v du. Okay, this one corresponds to the product rule. Okay, so this is corresponds to the product rule of differentiation. Okay, so let us recall what that is and then just see how this is working. Recall that the derivative of a product of two functions, f of x and g of x, is equal to f at x times g prime at x plus g of x times f prime at x. Okay, so that's the product rule from Calculus 1. Now let us imagine integrating both sides. Now integrate both sides. Okay, so I'm just going to go here like this, the integral, the integral, the integral, like that. And when I integrate the derivative here, I will simply get f of x and g of x. And then I will have here the integral of f of x g prime at x dx plus the integral of g of x f prime at x dx. So now all I'm going to do is rearrange that, and I'm going to move this term to the, well, actually what I'm going to do is write that term, and I'm going to move this term to the other side and then write it in. So I'm just reordering. Okay, this is just a small algebra step. So I have the integral of f of x g prime at x is equal to f of x g of x minus the integral of g of x times f prime at x dx. Okay, and that is what was in the box shaded above. So that is, it's easy to see that the integration by parts formula applies, and that it's legal to use it, and it is just corresponds to the product rule. Okay, let's see how to do this in practice. Okay, so let's start with the example we had on the previous page. We have to choose u, and we have to choose dv, and we have to cover the whole thing. So what I'm going to do is I'm going to sort of divide this into two pieces. One piece is going to be u, and the other piece is going to be dv. The whole thing has to be covered. You can't leave any pieces out. Okay, so let me try this. U is equal to x, and dv is equal to e to the x dx. Okay, so then if I have that, then I can compute du. Du will be, in this case, equal to dx, because the du by dx is equal to the derivative of x, which is 1. And then dv is equal to e to the x dx, and I integrate that. So I could be thinking of this like this if you liked to. dv by dx is e to the x, and then asking what is v. And that means here that v is e to the x. Okay, then I apply the integration by parts formula, the integral of x e to the x dx. Okay, that is going to be uv x e to the x minus the integral of v du. Okay, now I have an integral sitting there that I can do by inspection. So I get x e to the x minus e to the x plus a constant. So that is my integral of x e to the x dx. Okay, I could now check this by taking the derivative and making sure I did this correctly. So I'll take the derivative with respect to x of x e to the x minus e to the x plus c, and I'll see what happens. I'm going to use the product rule when I differentiate this, and I'm going to get e to the x, let's see, e to the x plus x e to the x minus e to the x, and then the derivative of the constant is 0. These two things cancel out, and I get x e to the x. Okay, it worked. Okay, so that is integration by parts. Now we have a choice when we pick which part of the integral is u and which part is dv. Let's just look what happens if I made the other choice. I could say, hey, why don't I try to make e equal to e to the x and dv equal to x dx. That's another legal option that covers the whole thing. That is opposite to what I just did in the first example. Then I would take the derivative here. I would get du is e to the x dx, and I would integrate dv by dx, and I would get that v is equal to 1/2 x squared. Then I would write out the integral x e to the x dx is equal to uv 1/2 x squared e to the x minus the integral of v to u. Okay, and you see that this is not wrong. Nothing is wrong. But you notice when I did this next step here, I ended up with something that was much simpler than the original, and something I could integrate by inspection. Here, I have ended up with something that is even, in fact, worse. So it's not wrong, but now I have a problem where, what am I going to do here? So I have not made any headway. So this is a key indicator. If you don't choose the parts properly and you end up with something more complicated, that's when you should think, maybe I should make a different choice. So really what you want is you want u going when I choose u, I want du by dx to be something simpler than u. Okay, so this didn't happen here. This stayed the similar complexity, and then when I integrated, it got worse. So I typically, and over here though, when I have du is equal to x, then when I took, if you look here, du by dx is equal to 1. 1 is a simpler function than is x. So that is the general sort of rule of thumb. You want things to get simpler when you're differentiating. It takes a little bit of practice to make the right choice, but if you don't make the right choice, you soon see that it is getting worse, and you should retreat back and try something else. Okay, let's look at another example. We want things to get simpler as we differentiate, and at first it looks like, what are we doing here? It doesn't look like there's enough pieces in some ways, but that is not the case. In fact, this is the standard way to determine what the integral of the log function is. And what we're going to do is we're going to divide it into two pieces right there, and we want whatever piece we differentiate to get simpler, and so I'm thinking of it like this, then u equals log x, and dv is equal to, say, 1 times dx. I could just put equal to dx, but just to get you the sense that there is a second function there if you like, and it is 1. Okay, so then when I take the derivative, I get here du is equal to 1 over x dx. And I get here, when I integrate, that v is equal to x. So then I employ the integration by parts formula. The integral of log x dx is equal to uv x log x minus the integral of v du. Isn't that nice? That is just the integral of dx, which is simply x. So this then becomes x log x minus x plus a constant. Okay, so I could, let me just write that up here. And then I'm going to just, this is sort of a, it's kind of a classic result, actually. You could ask yourself, we know how to integrate sine, cosine, e to the x and stuff. And then as soon as you go to integrate log x, if you don't know how to integrate by parts, it's actually not such an easy problem. So, and it's one of our elementary functions, so we should be able to integrate it. Okay, so I put the result there, and I can, of course, check. I'm not going to check too many more of these, but I will encourage you on when you're doing this to check what you've done to see if it's correct. And also on an exam, if you've got extra time, then definitely spend that time checking your answers. You can always take the derivative and you should get back to the function. So when I take this derivative, it should come back to log x. Let's see what happens. Employing the product rule here, I will get log x. And that is when I take the derivative of x times log x plus the derivative x times the derivative of log x minus the derivative of x, and then the derivative of the constant is 0. X over x is 1. 1 minus 1 is 0. So that is, in fact, log x. Okay, so it did work. Okay. We'll do another example that's in fact kind of similar here, and then we'll also would require an additional step. So we're here, it's not clear how to make much progress, but I mean the only possible division is here, and I'm already trying to integrate the arc sine, so clearly I have to set u to be the arc sine because I'm going to have to take I need to take the derivative of it to sort of simplify things for myself. So I'm going to choose u to be equal to arc sine of x, and then du will be 1 over the square root of 1 minus x squared dx. I will choose dv equal to dx, and then I will integrate, try to be consistent with my v's, dv equals to v dx, and then v will be x. Okay, I employ the by parts formula. The integral of the arc sine of x dx is equal to uv, that is x arc sine x arc sine minus the integral of v du, and that is x over the square root of 1 minus x squared dx. Now, I'm looking at this second integral here that I've just generated, and I see that, well, I think we've actually seen this one or something very similar already in this lecture series, but I see that this piece here is very closely the derivative here. So now I conclude that I should do this one by substitution. So I'm going to go on this by substitution. And I'm going to do the substitution u equals 1 minus x squared. And that means that du will be minus 2x dx. And that dx is equal to minus du over 2. Okay, so let me see here. Let's write it out this way. So this then will be, so what I'm doing here is saying that the integral of x over square root 1 minus x squared dx is going to be equal to the integral x dx. Let's see what is, oh, I lost the x over here. This is x dx. X dx is minus du over 2, and so this is 1 over square root u times du times minus du over 2. Okay, so this square root, I'm putting the u in here, and then x dx is minus du over 2. And so then I integrate that, and I get, let's see, minus u to the 1/2. So I'm taking 1/2 and then u to the minus 1/2. And then that is going to, what is u? U is 1 minus x squared. So that is there. And then then I can go back to my original integral that I was thinking about. So this right here was just a calculating that blue boxed in integral. And now I can write out the whole thing, and that's going to be that the integral of the arc sine of x dx is x arc sine x. And I've got minus minus, so that'll be plus 1 minus x squared to the 1/2 plus a constant. Okay. All right, this is a very powerful technique, actually. I want to see a couple of more flavors used in a slightly more complicated manner here. Yeah, we have an integral here. There's no obvious substitution, so I'm going to then divide it into 2 parts. I'm going to assign u to the part that seems to be getting simpler when I take the derivative, and dv to the rest of it. So that's going to lend me to choosing x equals x squared, at which point du is 2x dx. And then the rest of it is dv, which is e to the minus x dx. And I integrate that, and I get that b is minus e to the minus x. Okay, so the power got reduced here by 1, so it is simpler. It didn't maybe get completely easy, but let us see what happens when we write this out. So our original integral, x squared e to the minus x, is going to be equal to uv minus x squared e to the minus x minus the integral of v du. Okay, v du, and v is minus e to the minus x, and there's a 2 there, and so then there's an x dx. Okay, it's still not actually completely clear how I can, well, it's not that it's opaque, but I didn't get something that I can do by inspection here, but it is easier because you will notice here, there's a power. I mean, you can think there's a power of 1 there. We don't write that, but so the power has been reduced by 1. So I go ahead and do it again. Okay, well, it's very similar to the one we just saw now. So now I say, okay, that's fine. Don't give up. Proceed. U will be equal to x, and du will be dx. dv will be the remainder of it. So I'm dividing it here. Well, I have to be careful. I have to divide it there, actually. Let's see. Well, I'm dividing it like this, in fact. So the dv is e to the minus x dx. V is, like it was before, minus e to the minus x, like that. Okay, and so then I can just talk about this integral for a second, and then I'll put the whole thing together. So now I'm just going to look at this integral here, x dx. That is going to be u times v minus the integral of v du. There it is. Okay, then I'm in a much nicer position. You can easily now proceed with this by inspection. That is going to be minus x e to the minus x, and I'm going to integrate this here, which I can now do completely, and that is e to the minus x plus a constant. Okay, so now I just put all of these things together. The original integral, which was the integral of x squared e to the minus x dx, is equal to this piece here, minus x squared e to the minus x, plus 2 times this. Okay, so that I've got here this 2. I'm going to circle this. This 2. I'm going to go plus 2 times this, because that is what that integral is. So that gives me the x squared e to the minus x, and I get minus 2x e to the minus x minus 2 e to the minus x plus c. Okay, I recognize I didn't multiply the c by 2, but it doesn't matter. It's just some constant. If you want, I could call this one c1 and this one c2. They're not the same number, but we don't care. We just need a constant there, and we often just like lump all the comments together as one, and or if we multiply a constant by some other number, we don't care. It's just some constant, so we don't have to really keep track of that. But it is just a constant. It's some number. Okay. Right, so that's an example where you had to go integration by parts twice. Okay, here's the maximum difficulty coming, at least on sort of, I think really it is kind of the maximum difficulty, and we'll see a reduction formula come out of this. But let's get this example here and see what happens. We've got trying to integrate e to the 2x times cosine of 3x. It's not actually clear which is simpler by differentiating. I mean, if I differentiate e to the 2x, I get 2 e to the 2x. If I differentiate cosine 3x, I get minus 3 sine 3x. Which one of those is simpler? Not really clear. Okay, but what I do notice, I'm going to notice if I was going to differentiate twice. So I notice the following. If I take the cosine, I differentiate, I effectively get the sine. I know I'm missing negative and positive signs. And then when I differentiate again, I get back to where I started from. So noticing that little factor, I'm going to choose u to be equal to cosine of 3x. And then dv will be the rest of the integrand. So dv will be e to the 2x dx. Okay, and then I take the derivative, du, and that is minus 3 sine 3x dx. And then I integrate dv by dx, and I see that v is 1/2 e to the 2x. Okay, so I can then write the original integral, the integral of e to the 2x cosine 3x dx. That is going to be uv. Let's see, uv, which is going to be cosine 3x over 2 e to the 2x. That is uv plus, no, minus the integral of v du. And let's see what happens. V du, so I see a 3/2 there when I multiply v times du, and I see a negative sign, so I'm going to, that is plus 3/2, and I get e to the 2x sine 2x dx. Okay, don't give up. It looks similar. Actually, it looks like we haven't made much progress because we turned an integral that looks like this into one that looks like that, and I can't do that one by inspection either. But with this thing, this observation, I've gone from the cos to the sine. When I do it again, I'm going to get back to the cosine, and you'll see why this is helpful. So don't, the message here is don't give up. Let us take a look at this integral here, e to the 2x sine, this is sine 3x. That is a problem. Let me fix that. Sorry about that. I actually don't want to load sticky notes. Oh dear. Obviously held the pen down a little bit too long. Just a sec. Sorry, let me just get rid of that. Get rid of that. Closed notes are available. That's it. Got it. Oh, close. Bye-bye. Okay, so here, let me try again. There we go. I didn't press too hard. There, sine 3x. Okay, that is du. Okay, so now I'm taking a look at that integral. Sine, this one here, sine 2x, e to the 2x sine 3x dx. And I'm going to go by parts again, the same way, except this time u will be sine of 3x and du will be 3 cosine 3x. And dv will be the rest of the integral, which is e to the 2x dx, and v will be 1/2 e to the 2x. Okay, and then I can write out what the value of this integral is. That is going to be uv, that is sine 3x e to the 2x all over 2. That is uv minus the integral of v du. There's v, and there's du. So that's minus 3/2 the integral of e to the 2x cosine 3x dx. Okay. One of the things saying this is just going around and around in circles. This is actually what we started with, right? What we started with. Okay. Let me write this all out now. What I'm going to do is I have computed this integral here. I am going to put that right here. Okay? What I'm going to do is use what I figured out here back into there. So where am I at this point? I know that the original integral, this guy here, the integral of e to the 2x cosine 3x dx is equal to cosine 3x over 2 e to the 2x plus 3/2, and then I'm going to put this in for this integral. So here I get sine 3x over 2 e to the 2x minus 3/2 the integral of cosine 3x e to the 2x dx, like that. Is it getting worse? No, actually we're almost done, because look what I have here. I have something here, right here, and I have the exact same thing right here. So I can solve for that as an algebra equation. This just looks like this. A equals something plus 3/2 something minus 3/2 A. And I'm going to solve for A in terms of all that other stuff. So now it's an algebra problem. And then let me do that. I'm going to erase this so I can do this below, but that is what I'm doing. Okay, I am going to collect those two terms onto the other side. So I'm looking here, I got 3/2 and 3/2, it's negative. So I add 9/4 to 1 and I get 13/4. So I get 13/4 times the integral of e to the 2x cosine 3x dx is equal to the rest of the stuff. Cosine 3x over 2 e to the 2x, and then I'm multiplying that 3/4 in, 3/2 in, and I get 3/4 sine 3x e to the 2x. Okay, almost done, right? I have 3/4 of what I want equal to this, so I simply multiply both sides by 13/4. 13/4 of what I want. So I'm going to multiply both sides by 4/13. and I get this thing here. So I get my original integral, the thing I've been trying to find all along here, e to the 2x cosine 3x dx is equal to, and I multiply by 4 over 13, and I get this 1/13 times 2 cosine 3x e to the 2x plus 3 sine 3x e to the 2x plus some constant. There we go. So it sort of didn't look so good off the top, but when you recognize if you can get back to the original integral somehow in this thing, then this allows you to combine from both sides and solve for that original integral. That was sort of the maximum complexity in some sense of using integration by parts in this course anyway. Okay, so here we have a reduction formula. You can see this is the same kind of idea. We don't have the e to the x in here, but what we're doing is saying if we have an integral and we're trying to integrate cos to the some power, the nth power, we can write that as this portion here, and then another integral where the power here on the cosine function has been reduced by 2. And so let's just say n was, just say it was alarmingly large at like 10 or something like that. You would reduce it down, then the next one would be 8, and then you could do it again, it would be down to 6, and then it would be down to 4, and then it would get down to 2, at which point you would use the half angle identity. So you have some method of doing it. It would be a little bit time consuming, but having a reduction formula like this allows you to write it out and do many integration by parts, lowering the power on the cosine each time, and then eventually being able to get to a full solution. Okay, so we're going to actually prove this reduction formula. So in order to do this, what we have to do is do integration by parts. We're going to do integration by parts on the original integral, and in order to do that, we have to be actually just slightly clever, and that is the trick here is to think of cos n to the x as cosine n minus 1 to the x times cosine x. That's a true statement. So that is going to, and then that's how I'm going to split it apart. So I'm going to think of the cosine to the nth power like that, to the n as the cosine to the n minus first power times cosine, and then I'm going to split it that's going to allow me to split the integral in this way, the integrand in this way. I'm going to put u is equal to cosine n minus 1 of x, and then the rest of the integrand has to be covered by dv, so that's going to be dv is cos x dx. Okay, it's the integration by parts, but I separated the integrand in how I wanted to, so I'm allowed to do that. Okay, so now I'm going to take the derivative, du. Du is going to be n minus 1 cosine n minus 2 of x times the derivative of the inner function, which is cosine, so that's minus sine x, and then that's dx. And then I'm going to integrate v, I'm going to integrate the cosine, and I'm going to get the sine. Okay, so now I can write this out. The integral of cos n x, cos to the nth power of x dx is equal to, well, now I'm doing integration by parts, so this is uv, so I get cosine n minus 1 x times sine x minus the integral of, let's see, the integral of v du. So I see there's a minus sign, so that'll be a plus, and that is going to be n minus 1. And then what have I got left? I've got cos n minus 2 of x dx times, whoops, well, I want to move the dx to the end, but I'm multiplying v times du, and I've got a sign there and a sign there, so that's going to be sine squared x dx. I haven't quite got that formula sitting up there yet, do I? Okay, so what am I going to do right now? I'm going to say but, recall the trig identity, sine squared x equals 1 minus cos squared x. So that means that I can rewrite this here. Let's using that identity. Cos to the nth power of x dx is equal to cosine n minus 1 of x sine x, that is the same, plus n minus 1. And here I'm going to replace the sine with using that trig identity. That's the cosine n minus 2 of x. And then the sine squared, I'm going to replace it with 1 minus cos squared x dx. Okay, let's see what's happening. Here I'm going to be cosine, I'm going to complicate that with a bracket, cosine to the nth power of x dx equals cosine n minus 1 of x times sine x plus n minus 1. And I'm going to separate these integrals. So this will be cosine n minus 2 of x. That's multiplying this cosine times the 1, and then multiplying the cosine times the cosine squared. And that's going to give me here cosine of to the nth power. Okay, and I'm in a similar situation of that situation I had earlier, and that is I've got this piece here to be the same as this piece here. So I can shuffle those things over and add them together. I've got, I have one of them here, and I have n minus 1 of them there. So over here, I would have 1 plus n minus 1, and that is going to be multiplied by this cosine to the nth power of x dx, and that's going to be equal to the rest of this stuff. Cosine n minus 1 of x sine x plus n minus 1 times the integral cosine n minus to the n minus second power dx. Okay, I'm getting really close. So now I've got to do is just divide both sides by this here. So we've seen two examples now of when you end up with something on the same integral on both sides, allowing you to move it and combine. That is going to be cosine to the n minus 1 x sine x over n. Oh yes, dividing by this n right here. Just make sure I saw where that n is coming from. Plus n minus 1 over n times the integral cosine n minus 2 of x dx. Okay, and we've now shown that indeed that statement above is a true statement. Voila. That is not exactly what you're supposed to write at the end of the proof, but it's kind of a nice result. So there's a little bit of subtlety here, but the basic integration by parts is fairly straightforward. You need to do, I don't know, some number of them, 50 or something like that, and then it becomes sort of routine and you don't have to think about it. In fact, you do want to kind of get as many things into that sort of routine mode. Like, you know how when you first learn how to drive a car, you're thinking, my God, you're tired. You've gone out for like, half an hour of driving practice and you're exhausted and have to lie down for the rest of the day. And then after you've been driving for a few years, you kind of drive around without thinking about it. You want to do enough of this too, so that certain portion of it just goes into your brain as like sort of driving around without thinking about it. Doesn't tire me out, doesn't take up much time, and I can work quickly. Okay, so let's just try to use that reduction formula. This is going to be totally straightforward. The integral of cos squared x dx This is obviously the case with n is equal to 2. So I can immediately write down that this is 1/2 using the formula cos x sine x, like that, plus 1/2 the integral, and I reduce the power by 2, and cosine to the 0 is 1. So then I would not recommend memorizing the reduction formula. This is just to see how these things are produced using integration by parts and getting some skill. I will not require you to have, do not memorize this. I would never be able to get that out of my head. If somebody asked me what it was, I would go through the procedure that I just showed you and regenerate it. Okay, I can integrate that easily, so then I can tell you that the integral of cosine squared of x dx is 1/2 cos x sine x plus 1/2 x plus a constant. Okay, that's just a basic use of the formula. That just took us quite a bit of time to develop. Let's just use it one more time, just so we're sure of what we're doing here. We got the same problem. We got given the reduction formula, and we're going to actually use parts A and B, and we're going to do it when n equals 4. Okay, so no, this is straightforward. Stop the video, maybe see if you can do it, and if you can, then say, okay, good, I've got that. Fast forward through this little section, and then you're done. Okay, so what am I doing? I'm using the formula. N is 4, so there's 1/4, and n is 4, so n minus 1 is 3. Then I'm multiplying by the sign, and then n is 4, so this is going to be plus 3/4 times the integral of cos squared x dx. Okay, and I just did that in the last slide, so no use to go through that again. I will simply port that little result forward. So this is cos to the 4th power of x dx, and that is 1/4 cos cubed x sine x plus 3/4, and then I have that result from last time, which is this here. There you go. Okay, so we can now evaluate any number of those that we would like to do so. Something to do, hey, on a Saturday night. Okay, all right, let's do one final example here, and then we will be done with integration by parts. So here we've got we want to evaluate the arctangent between x equals 1 and x equals √3. We are going to do this by parts, and there's only one way I can divide this up, and that's like that. And so that means that I'll have to put either u or v to the arctangent, but I'm clearly not going to want to integrate the arctangent, so it's going to have to be u. So I'll put u to be arctangent of 1 over x, and that means that du will be the derivative of the arctangent, 1 over 1 plus the argument squared, like that, multiplied by the derivative of the inside, which is minus x to the minus 2. Okay, and then dv will be dx, and v will be equal to x. Okay, in case it hasn't been blindingly obvious as we've been going along here, you have to be able to take derivatives in order to integrate. So if I can't remember how to take the derivative of the arctangent, or I don't remember the chain rule for differentiation, I am dead in the water. Okay, so any of these steps where you're thinking, okay, she's taking the derivative, but I don't remember how to do that, now is the time to fix that, because we're sort of building on your previous skills, so you definitely need to know how to do this here. Okay, so what are we going to do? Let's see. So our integral, let me just call this a. So a is going to be equal to uv, that is x arctangent 1 over x evaluated at 1 and √3. So we're doing a definite integral, so we're going to be coming out with a number, and then or we'll have the integral from 1 to root 3 of v du, which is, let's see, that'll be, this will turn to a plus, and that will be x times x to the minus 2. That gives me x to the minus 1, and 1 plus 1 over x squared dx. Okay, and keep going here. This is going, then I can do this evaluation. That's going to be root 3 times the arctangent of 1 over root 3 minus the arctangent of 1 plus this integral here, which maybe I'll just rewrite a little bit, 1 to root 3 1 over x times 1 plus 1 over x squared dx. Okay, so I've got part of it done. Now I have the problem of evaluating this thing here. Let's do that separately. So a is equal to this, and now I'm going to take a look at that integral there. Now the arctangent is gone, so I feel a little bit of hope based on that. I'm going to multiply that x in. I'm going to get x plus 1 over x, like that, dx. What am I going to do then? I'm going to make a common denominator, and then, well, here, you'll see what I'm basically playing around with fractions here. I'm going to rewrite this as x over 1 plus x squared dx. Okay, so this is just fraction manipulation. Okay, and now I'm in a situation where I'm not completely done quickly. On the other hand, I can clearly see that the x in the numerator there, let me make that in a different color. This x here in the numerator is the derivative, most basically, so to speak, of the denominator. So I'm going to make a substitution. I'm going to substitute like this. Let u equals x squared plus 1, and then du will be 2x dx. Now, so this is our substitution, and then of course when we're substituting, we have to do a complete substitution, including the limits of integration. So I'm going to take that into account. When x is equal to 1, u is 2. 1 squared plus 1 is 2. And when x is equal to square root of 3, u is going to be equal to 4. Square root of 3 squared is 3. 3 plus 1 is 4. Okay, so then this is going to be equal to the integral from 2 to 4 of 1/2 du over u. Okay, x dx is du over u. Sorry, yeah, x dx is du over 2, and then 1 over 1 plus x squared is 1 over u. Okay, this is easy to integrate. This is going to be 1/2 the log of u evaluated at 2 and 4. And then when I do that, I get 1/2 log 4 minus log 2. Okay, so now I have that result that I have now computed this integral right here, and I can put all this stuff together. So my original question, which I called A, the original integral I wanted to do, is going to be, I have to put all these things together. That was pi times root 3 over 6 minus 1/4. And then this new stuff that I figured out, plus 1/2 times the log of 4 minus the log of 2. There it is. Okay, so that's the that is the final answer. Okay, sort of in our calculator form. We actually probably, I mean, particularly this here, we might be able to simplify a little bit more, but this is indeed a numeric answer. Okay, folks, that is integration by parts. We will be back next time with our next tactic. I'm just checking what it is. What is our next tactic? Trigonometric integrals. So we're just getting a little bit more skill at evaluating these integrals right now. Thank you.